Welcome to part 7 of the Ontario High School video podcast series having to do with acid-base fundamentals. This particular podcast will address the acid-base properties of metal cations. So stay tuned. We'll start with some undeniable truth. So, undeniable truths. Cations of group 1A metals. That's group 1A, can be a Roman numeral 1A, can just be 1A as I've written it here, or 1 out of 18 depending on what periodic table you're looking at. These are sodium, potassium, rubidium, cesium, francium, and lithium. And the more massive cations of group 2A, calcium, strontium, and barium ions, Ca2+, Sr2+, and Ba2+, these do not affect pH when they're in water, and these, I guess, coincidentally, can best be described as cations of strong bases. So other metal cations, however, will cause a decrease in pH, and that's what we're going to look at in this podcast. Well, we should have a rationale for all that we do, or all that we think. So here's the rationale for the acidic behavior of metal ions. It's explained best by Lewis acid-base concept. Remember, Lewis acids are electron pair acceptors, and Lewis bases are electron pair donors. So what happens in solution is that these positive metal ions attract unshared electron pairs of water molecules, and the unshared electron pairs in the water molecule are not on hydrogens, they're on the oxygen of the H2O. This interaction, which we know as hydration, is what is responsible for the dissolving of the metal cations when they're part of a salt. So this is a very important aspect of Lewis acid-base behavior, one that we'll need to pay close attention to. So metal ion acts as a Lewis acid, the water molecule acts as a Lewis base. The electron density, or the charge density, is drawn from the oxygen atom in the water molecule toward the positively charged metal cation. This increases the polarity of the hydrogen-oxygen bonds in the water molecule. The water molecules bound to the metal ion then become more acidic than the rest of the water molecules in the solvent. Now, we have learned when we have done our net ionic equations, and as we've looked at describing the dissolving process of ionic compounds, we usually represent metal ions in solution as just the formula with its charge and aqueous for its phase. In reality, when iron 3+ dissolves in water, it becomes surrounded by water molecules and is more precisely written as Fe, then in parentheses H2O with a subscript 6 and a 3+ charge. And this is what acts as a source of protons in the following way. So we have this FeH2O6 with 3+ charge forming FeH2O with a subscript 5 OH 2+ and ionizing one of the H pluses from the H2O. So that's the reaction that you see here, and the Ka for this reaction is pretty big. It's 2 times 10 to the negative third, which is for instance 2 orders of magnitude stronger than a weak acid we're real familiar with in acetic acid. So Fe3+ aqueous is a fairly strong acid. So as we continue to look at the behavior of iron 3+, the hydrated iron 3+ in solution, the Ka for this again is 2 times 10 to the negative third. So the iron 3+ aqueous is a fairly strong acid. Remember that acid dissociation constants, the Ka values, generally increase with increasing charge and decreasing radius of the ion. So we can predict when we're comparing metal ions and their acidic behavior, the ones with greater charge, like 2+ or 3+ as opposed to 1+, and a smaller radius, the smaller metal cations with the higher charge have a stronger charge density and will have a stronger acidic behavior in solution. So as a way of comparison to the hydrated iron 3+, let's look at a hydrated copper 2+. This is a metal ion with a larger radius than the iron 3+, and a smaller charge than the iron 3 plus, it's 2 plus rather than 3 plus, it has a much smaller Ka value, thus a much less acidic behavior. And look at the Ka for the hydrated copper 2 plus is 1 times 10 to the negative eighth. Well, based on their Ka values, and again a general trend toward the higher charge and smaller radius ions having more acidic behavior, we want to look at some other factors that affect acid strength. So first we're going to look at binary acids, and we're going to represent these with a general formula of Hx, where X will be the anion that the hydrogen is bonded to, the nonmetal that the hydrogen is bonded to. Remember, when hydrogen is bonded to metals, it doesn't have an acidic behavior, only when it's bonded to nonmetals. So the most important factor is the bond between the hydrogen and the atom represented, or element represented by X, in which X is in the same group on the periodic table. So for instance, when we look at the halogens, they would include chlorine, bromine, and iodine in terms of the strong acids from the halogen group. As bond strength decreases as one moves down a group, and as bond strength decreases, acidity increases. And this should make sense to us because the weaker bond strength between the hydrogen and the nonmetal element that it's bonded to means that the hydrogen can be released more easily or taken away more easily. So HCl is a stronger acid than HF. H2S is a stronger acid than H2O. So again, remember, bond strength decreases as one moves down a group, so the acid strength would increase as you move down a group. Now, it's very easy to predict the strength of an acid by its bond strength when you're looking at the elements that hydrogen's bonded to when they're in the same vertical group or column on the periodic table, the same family. But bond strengths change less when we move left to right across a period than when we move down a group. So rather than bond strength, the bond polarity becomes the major factor in predicting the acid strength. And the bond polarity is based on the electronegativity difference between hydrogen and the nonmetal that it's bonded to. So acidity increases as the electronegativity of the element represented by X increases. Thus, HCl is stronger acid than H2S, since Cl is more electronegative than S. So if you're given two acids, binary acids, from side-by-side non-hydrogen elements that the hydrogen is bonded to, you would predict that the stronger acid will be the more electronegative element, which is to the one to the right on the periodic table. Well, let's look at factors that affect the acid strength of acids that contain polyatomic ions as the anion, and these also often are oxyacids. So let's look at those. The general formula here is H sub A, Y representing the non-oxygen part of the polyatomic ion that the hydrogen is bonded to, and then of course O representing the oxygen. Now, oxyacids contain one or more OH groups. For instance, H2SO4 has two OH groups. And here's something that's real important to remember. When you have an acid like H2SO4, the hydrogens are not bonded to the sulfur. They're bonded to the oxygen atoms. So you have two hydrogens there. So you'll have, in this formula unit, you'll have a hydrogen on each of two different oxygens in the H2SO4. So H2SO4 has two OH groups, H3PO4 has three OH groups, HClO has one OH group. Hydrogen atoms that are not bonded to the central atom, in these examples the sulfur, phosphorus, or chlorine, they are bonded to one of the terminal oxygen atoms in the polyatomic ion. That's critical to understand. As we look at the element represented by Y in our general formula, here's how we want to predict the strength of the acids. As the electronegativity of the central atom represented by Y increases, the acidity of the compound increases. This is because with the increased electronegativity of Y, the electron density is drawn toward Y, which weakens the outlying oxygen-hydrogen bond, increasing polarity, and this favors the loss of the H+. Since the conjugate base is an anion, its stability increases as the electronegativity of Y increases. And again, we can describe the loss of the H+ as the ionization of H+ in aqueous solution, and that is acidic behavior. The strength of oxyacids also increases as the number of oxygen atoms attached to the element represented by Y increases. These additional oxygen atoms pull electron density from the OH bond, increasing its polarity and the likelihood of ionizing the H+. So here we're looking at oxyacids that have the same element represented by Y. For instance, on the next slide you're going to see four oxyacids that have Y as chlorine, and you'll see the difference in the acid strength based on this principle. So here we have four oxyacids, of which chlorine is the element represented by the Y in the general formula. We have HClO, which is called hypochlorous acid, HClO2, which is chlorous acid, HClO3, which is chloric acid, and HClO4, which is perchloric acid. So let's look at the Ka values here. You can see that for HClO, and oftentimes you will see this written HOCl, which puts a more structural look at what this acid really looks like, because the H is put with the O, which it is in reality. But the Ka value for that is 3 times 10 to the negative 8th. When we add one more oxygen to this, HClO2, the Ka value increases to 1.1 times 10 to the negative 2nd. When we add 2 more oxygens to this, HClO3, it's a strong acid and ionizes 100%. And then finally, HClO4, perchloric acid, also a strong acid that ionizes 100%. So the greater the number of oxygens, the stronger the acid will be. And when we look at 2 other acids, for instance, H2SO3, sulfurous acid, and H2SO4, sulfuric acid. Sulfuric acid is a strong acid that ionizes the first hydrogen 100%. H2SO3 is a weaker acid. So things that we can predict when we're given acids to compare in terms of strength and how to predict. Let's just compare H2SO4 and H3PO4. Both have the same number of oxygens, but the H2SO4 has a greater number or a greater ratio of oxygens to hydrogens. You see it's 2 to 1 compared to H3PO4, which is 4 to 3. And it also has a more electronegative element that the oxygens are bonded to. Sulfur is more electronegative than phosphorus. So H2SO4 is a strong acid, H3PO4 is a weak acid. S is more electronegative than P. The greater the electronegativity of the Y atom in the oxyacid, the stronger the acid behavior. Well, we've come to the end of part 7 of the video podcast series dealing with acid-base fundamentals. We dealt in this video podcast with the factors that affect acid strength of both binary acids and acids that contain oxygen in a polyatomic anion setting. And we also dealt with the acidic behavior of metal cations. I want to leave you with a quote from the famous author Miguel de Cervantes. He preaches well that lives well, and I wish you well.